Hey guys, in this video we're going to talk about the shapes of molecules, and we're going to do it with balloons. Stick around. You might recall back in Chapter 5 we talked about electron configurations and orbital diagrams, and we're going to use that just a little bit to talk about what we need to today. First off, let's take a look at a carbon atom in terms of its orbital diagram when it's not bonded to anything. We would expect it to be something like this, where you have, of course, the 2 electrons in the 1s orbital, the 2 electrons in the 2s orbital, and 2 electrons in the 2p sublevel. But the thing is that carbon doesn't just hang out by itself, it will actually bond to other things. And when it does this, it does something fascinating with its orbitals. Let's say that carbon's going to bond to 4 different atoms, like in the case of methane, CH4, where carbon is the central atom and it's bonded to 4 hydrogens. Now what we find experimentally is that those 4 bonds, those 4 carbon-hydrogen bonds in methane are all equivalent, which doesn't make sense if your valence electrons are at different energy levels in the carbon. Instead, carbon undergoes something called hybridization. So when it undergoes hybridization, it takes that 2s orbital and all 3 of the 2p orbitals, blends them together, and makes 4 equal energy orbitals. And it will put an electron in each one of those. Each of those is suitable to make a sigma bond with something else. In the case of methane, a hydrogen atom sigma bonds with each one of those orbitals. These orbitals now have a different name. We don't call them s orbitals anymore or p orbitals anymore, but rather we call these sp3 orbitals. You could think of it as an ingredients list. To make those 4 orbitals, carbon took an s orbital and 3 of the p orbitals, blended them together, and made 4 equal energy orbitals out of it. Imagine that this is the carbon atom. You're also going to have to imagine the 2s orbital located within these other orbitals. These would be the p orbitals on the outside. A p orbital in yellow, a p orbital in red, and a p orbital in blue. So when carbon is going to sigma bond 4 times, it takes the s orbital inside and these p orbitals, blends them all together, and makes 4 equal orbitals, 4 equal areas of electron density. Each of these is capable of sigma bonding with another atom. So essentially this is what methane looks like. You've got carbon in the middle with its electron density in these sp3 orbitals overlapping with the electron densities of the hydrogen atoms. Here's the other interesting aspect of this model. It actually illustrates for us another principle that we see with electrons and how they arrange themselves in a molecule. Electrons like to give themselves plenty of space, plenty of elbow room as it were. In the case of the Lewis structure, we might consider that methane is simply a cross shape with 90-degree angles between the bonds. But that's not actually the case. The electron densities in methane are going to move themselves as far apart as possible. We can see this illustrated with the balloons. If I try to push them into a cross shape, there's tension there, and the balloons don't like to be in that shape. They would much rather revert back to the tetrahedral shape. And the angle between each of these is not 90 degrees, but actually 109.5 degrees. No matter which way I turn it, each of these is going to be 109.5 degrees. That tells us that that's as far apart as 4 electron densities can get, pushing themselves away to the point where they're 109.5 degrees apart. We can see that the shapes of these molecules are dictated by the way that the electrons push themselves apart. They repel each other. This concept is what we call VSEPR, or valence shell electron pair repulsion. This theory helps us to understand why the molecules are shaped the way they are. This shape has a special name. We call this tetrahedral. The tetrahedral shape involves 4 regions of electron density. So whenever you have an atom that has 4 areas of electron density around it, we call that sp3 hybridization. That even works if there are non-bonding pairs of electrons involved, like in the case of water. In the Lewis structure for water, we can see that oxygen forms a total of 2 sigma bonds with 2 different hydrogen atoms. But it also has 2 leftover pairs of non-bonding electrons. Those are also regions of electron density. So when the oxygen hybridizes its orbitals in the water molecule, it makes 4 equal energy orbitals, and it fills those 4 orbitals with 6 electrons, just like you would with Hund's rule. So 2 of the orbitals already have 2 electrons. Those are the 2 unshared pairs of electrons on oxygen. The other 2 are ready for sigma bonding. This helps us to visualize what's going on with the water molecule. If the oxygen is in the middle here, it has 2 sets of bonding electrons, one going to one hydrogen and one going to the other. And then it has 2 leftover non-bonding pairs of electrons. You can see that since it has 4 regions of electron density, we have that tetrahedral shape, even though only 2 of the pairs of electrons are involved in bonding. This is still what we call sp3 hybridization. As far as the geometry goes of these molecules, we actually consider them in 2 different ways. One way we call the electron domain geometry of that molecule. In the electron domain geometry, we're talking about all the electron domains surrounding the atom in question. But the second way is what we call molecular geometry. It's a little bit different than electron domain geometry in that we only consider the bonding electrons involved. To illustrate the difference, let's talk about methane again for a second. Here we have sp3 geometry, right? This tetrahedral geometry. In the case of methane, we have 4 domains of electrons, which gives us an electron domain geometry of tetrahedral. And in the case of methane, the molecular geometry is also tetrahedral, by virtue of the fact that all 4 domains are bonding domains. Now let's look at the water molecule. The oxygen would be in the middle here, with a pair of bonding electrons going to this hydrogen, and another bonding pair of electrons going to this hydrogen. Then we have 2 pairs of non-bonding electrons on the oxygen. Since the oxygen has 1, 2, 3, 4 regions of electron domain or electron density, we would say that it has an electron domain geometry of tetrahedral. However, when we look at the molecular geometry, we only take into account the bonding electrons. The molecular geometry of the water molecule is what we call a bent molecule. If you've ever wondered why water is a bent molecule, if I hold it in this shape, it doesn't stay there for long. It will actually revert back to this bent shape because of these 4 domains of electrons that push each other as far apart as possible. Here's another example of where we have a molecule that has a tetrahedral electron domain geometry, but the molecular geometry is different. This represents the molecule ammonia, where you have nitrogen with 3 sigma bonds going to 3 different hydrogen atoms with 1 leftover pair of unbonded electrons. Those unbonded electrons count as an electron domain. Therefore, you have 1, 2, 3, 4 domains of electron density. So yes, the electron domain geometry of this molecule is tetrahedral. With ammonia, even though one of these domains is not a bonding pair, this bonding pair still forces the other 3 pairs into a tetrahedral shape. Because of that, the bonding angles here are going to be really close to 109.5, as they are with any electron domain geometry of tetrahedral. In this case, they're really close, around 107. Since it's tetrahedral, we still say that it has sp3 hybridization. But the molecular geometry is not tetrahedral. We only consider the bonding electrons, don't we? This additional pair of unbonded electrons serves to repel the other 3. So it doesn't have a trigonal planar shape. Rather, it pushes it into a pyramidal shape. Therefore, we call this trigonal pyramidal. So, to sum up this section, anytime we have 4 regions of electron density around an atom, we say that that atom is sp3 hybridized and has an electron domain geometry of tetrahedral. What happens though if carbon only makes 3 sigma bonds with 3 different atoms and also forms a double bond with one of those atoms? In that case, we have a different kind of hybridization that occurs. If carbon is only going to make 3 sigma bonds, that means it only needs to hybridize 3 orbitals. So it will do just that. It will take the s orbital and 2 of those p orbitals, blend them together and make 3 equal energy orbitals, and then it will have that 1 p orbital left over. It places an electron in each one, and whereas when we had 4 equal energy orbitals, we called that sp3, this time we're calling these orbitals sp2, by virtue of the fact that we used an s orbital and only 2 of the p orbitals. So when carbon undergoes sp2 hybridization, it has 3 equal energy orbitals capable of forming sigma bonds with other atoms, and then it has one leftover p orbital. That p orbital will be used to make a pi bond, a double bond, with another atom. To illustrate this, I've made two carbon atoms that have undergone sp2 hybridization. These two sp2 orbitals can overlap to form a sigma bond. That means that the leftover p orbital on this carbon will form a pi bond with the leftover p orbital on this carbon, like so. I'll show you different angles of this, but here we can see the pi bond in position. You can see the orange sigma bond in the middle of these two carbons, with the pi bond going above and below. And if I turn it this way, you can see the other sigma bonds that are available on these carbons that have undergone sp2 hybridization. These sigma bonds, for example, could overlap with hydrogens, as could these sigma bonds, and form what we call ethene. It's where we have a carbon-carbon double bond with two other hydrogens sigma bonded to each carbon. Carbon 1, carbon 2, each of these carbons has 3 sigma bonds involved and 1 pi bond involved. sp2 hybridization. I'm going to hold it from this angle to show you something else. These 3 hybridized orbitals, these sp2 orbitals, all form a triangular shape, don't they? And they're also in the same plane. Do you see that? If we take our plane and move right through here, all 3 of those orbitals would be in the same plane. So imagine the sp2 hybridized orbitals without the leftover p orbital, and this is what you get. You get a triangular shaped set of orbitals that are all in the same plane. We call this shape trigonal planar. Trigonal because it has that triangular shape, and planar because they're all in the same plane. Something else about this is that you have 120 degrees between each bond. 120 degrees here, 120 degrees here, and 120 degrees here. That's as far apart as those electron densities can push to give them the most stability. So whenever we have 3 regions of electron density around an atom, even if one of those densities is a double bond, we call that sp2 hybridization. And sp2 hybridization is characterized by that trigonal planar shape. You can see it in this diagram of ethene, where each carbon has 3 areas of electron domains surrounding it. 2 of the domains are sigma bonds going to the hydrogens, and the third domain is the double bond going to the other carbon. 3 total domains giving us sp2 hybridization. So, anytime you have 3 regions of electron density or electron domains around an atom, that is sp2 hybridization, and the shape is going to be trigonal planar. Let's see what happens though when carbon forms 2 sigma bonds and 2 pi bonds. In this case, carbon only needs to hybridize 2 orbitals. It will hybridize one of the s orbitals and one of the p orbitals, forming, you guessed it, 2 equal energy sp orbitals, with 2 p orbitals being left over in the process. We'll represent it with these balloons. In this case, the red balloons represent the 2 hybridized sp orbitals. Then you have a leftover p orbital in yellow and a leftover p orbital in blue. So if I have this sp hybridized carbon and it gets together with this sp hybridized carbon, they can only form 1 sigma bond, the overlapping of one of the sp orbitals here and the sp orbital on this carbon. So then those leftover p orbitals are going to pi bond, like so. Here we have the end result. I'll pull the yellow balloon away a little bit so you can see the red sigma bond in the middle, the result of the sp orbital from this carbon overlapping with the sp orbital on this carbon. The blue pi bond is a result of the overlap of one of the p orbitals left over on this carbon and one of the p orbitals left over on this carbon. And then the yellow pi bond is a result of the other leftover p orbital on this carbon overlapping with the other leftover p orbital on this carbon. sp hybridization. By the way, the other sp orbital is available to sigma bond with another atom. In the case of the acetylene molecule, we can see that that sigma bond goes toward bonding with another hydrogen, like so. As far as the shape goes, other than looking like a hot dog, this molecule is fairly linear, isn't it? That's exactly what we see in sp hybridization, a linear shape. In the case of this carbon here, we have 2 regions of electron density, one here and the other here. Even though it's a triple bond, it still counts as 1 region of density. Again, whenever you have 2 regions of electron density around an atom, that gives you a linear shape and sp hybridization. In our last video, we talked about some instances of when the octet rule is broken. One example of that is phosphorus pentachloride, PCl5. So how is phosphorus able to break the octet rule? Let's look at phosphorus's orbital diagram and figure this out. As we did with carbon, we're just going to look at the outermost energy level, the third level. So we see that phosphorus has 2 electrons in the 3s orbital and then 3 electrons in the 3p sublevel. So it has a total of 5 valence electrons available for bonding. And we know that it does this with PCl5. So how is it able to hybridize in such a way? Phosphorus is in period 3. As we mentioned briefly in the other video, elements that are in period 3 or greater have the advantage of a d sublevel. So in the case of phosphorus, it will hybridize using the s orbital, all 3 of the p orbitals, and 1 of the d orbitals to make 5 equal energy orbitals that are called sp3d orbitals, giving phosphorus 5 regions of electron density. So it looks like this. You can see 1, 2, 3, 4, 5 regions of electron density around the phosphorus. Each of these orbitals is able to sigma bond with another atom, such as chlorine. Whenever then we have an atom with 5 regions of electron density, we say that that atom is in sp3d hybridization. As far as the shape goes, we call this trigonal bipyramidal, or 2 pyramids. Look at it this way. It looks like we have a pyramid here and a pyramid here, and those pyramids are base to base. The base of the pyramid is triangular shaped, trigonal bipyramidal. In this trigonal bipyramidal shape, we have 2 sets of bond angles. For these regions of electron density in the middle, if we turned it up this way, we can see that there's 120 degrees between each one. The ones on top and on bottom form a 90-degree angle with the domains in the middle. That's as good as these electron domains can do to push themselves as far apart as possible. So again, whenever we have 5 regions of electron density, that's sp3d hybridization with an electron domain geometry of trigonal bipyramidal. Let's go one more. Take the case of sulfur hexafluoride, for instance. How can sulfur form 6 sigma bonds with 6 different fluorides? Well, you may have already guessed, but let me show you anyway. Sulfur is also part of period 3, and therefore has access to that d sublevel that we talked about. Sulfur has 6 valence electrons that, if rearranged, are available for sigma bonding. So sulfur does just that. Sulfur takes its outermost s orbital, the 3 p orbitals, and 2 of the d orbitals, blends them together, and makes 6 equal energy orbitals. In the case of sulfur hexafluoride, the fluorines can come along and sigma bond with each one of those new orbitals. This hybridization is called sp3d2 hybridization. Here's the result. An atom that has 1, 2, 3, 4, 5, 6 domains of electrons around it, and each region capable of forming a sigma bond with another atom. This shape is called octahedral. And you may be wondering why octahedral. Why not something with hexa in it? The word octahedral means 8 faces. Let me show you how that applies to this shape. If we look, we see 2 pyramids again. One here and one here. This time, though, we have a square base. So each pyramid has 1, 2, 3, 4 faces on it. So 4 faces on top, 4 faces on bottom, 8 faces. Octahedral. For the octahedral shape, every one of the bond angles that we see on here is a 90-degree angle. It doesn't matter which way you look, each one of those bonds will be 90 degrees apart from the other. Therefore, anytime we have 6 regions of electron density around an atom, we say that that atom is in sp3d2 hybridization and has an electron domain geometry of octahedral. By the way, you may be thinking, big deal. Shape? Really? Sometimes shape can be everything in chemistry. Whether it's how a sugar molecule can engage with a taste bud receptor. All of that has to do with the shapes of the molecules. In other words, any old shape isn't going to do. The things that occur inside your body are very much like a lock and key, where one molecule has to fit perfectly with another molecule in order to make something happen. And I want to tell you again, you are not an accident. In the same way, we would never expect that a lock and key, with all its complexity, would come together on its own. You should know that the parts of your body were engineered. As David said, God knit us together while we were still in the womb. And David also said that we are fearfully and wonderfully made. That's all we're going to do for this video. Today we talked about the principles of hybridization and valence shell electron pair repulsion theory, how we can use both to determine the shapes of molecules. I know that there was a lot in this video, and I hope it's been helpful to you. If I can explain any further, please let me know. Until next time, God bless.